So we have come to an end of the lecture series on thermodynamics, and we wind it up with the beautiful Carnot engine. Carnot we write and we read it as Carnot. So Sadi Carnot, he was a French engineer, and in 1824, around 200 years before, he studied the various possibilities of obtaining an engine operating between two reservoirs at two temperatures, T1 and T2 respectively. And he studied without knowing the laws of thermodynamics which came on later. And he came out with the beautiful idea that the eta can be maximum only by means of what is his Carnot engine. Now, his goal was to obtain the efficiency to be maximum. I've talked to you about eta, that it cannot be 1, it has to be less than 1, but still now we have to see as to what is the condition that eta may be ideally maximum. So we have to look at the processes that have to be adopted to obtain a situation like this. Well, we expect ideal reversible engines working between the two reservoirs at the two temperatures T1 and T2, and that engine has to be a reversible engine. Okay. Irreversibility is associated with dissipative effects. So, if we have a system like this, where we have the reservoirs at temperatures T1 and T2, and in between there is an engine and work is being done by the engine. Okay, so in this situation, in this schematic, there is irreversibility that will crop up time and again. Okay. Well, any process is not quasi-static if delta T is finite. What should be the value of delta T? The temperature difference between the two reservoirs. Delta T should be infinitesimally small. So, for a reversible engine which operates between the two reservoirs at temperatures T1 and T2 respectively, the heat absorbed or released has to be, the process has to be an isothermal process. So how to complete the cycle T1 is to T2 and back from T2 to T1? How come? Then the suggestion is we can adopt reversible adiabatic processes, wherein in adiabatic process delta Q is equal to 0. There is no transfer of energy, okay, heat energy. Heat cannot enter, heat cannot exit out of the system which we take for the process. The delta Q should be equal to 0. This is we have learnt about the adiabatic process. Now, for example, if we choose instead to use isochoric process, isochoric means the volume has to remain unaltered, unchanged. So what we need is a very large number of reservoirs at temperatures varying very small from T1 to T2. Okay. To ensure that each stage is quasi-static. Each stage is quasi-static and the delta T should be very, very small. Now, to sum it up, we need two processes. One is the isothermal process and the other is the adiabatic process, and that is what results in a Carnot engine between the two reservoir temperatures T1 and T2. Carnot engine, but we call it Carnot engine, Sadi Carnot. So, in the proposed engine by Sadi Carnot, anybody could have arrived at this result, and the working substance has to be an ideal gas. PV is equal to nRT. Okay. Now let's see as to what steps have to be taken. So there I marked 1, 2, 3, 4. So 1 to 2 is one step, 2 to 3 is another step, 3 to 4 is another step, and the last step brings it back to its original set of macroscopic variables. We define the thermodynamic state of the system, and from 4 to 1 and back to the pavilion. Okay, जैसे थे, right? So the first process that is proposed is from 1 to 2. This is an isothermal expansion. You can see that the volume of substance increases, so it is an isothermal expansion. The temperature has to be the same. Okay, and a new set of P1 from P1 V1, new set of P2 V2 is obtained in this process. Heat absorbed gas, which is Q1 from the reservoir, which is also equal to the work done on the environment. This is we have already done it, and this was arrived at like this, where N is the number of moles in the gas, R is the universal gas constant, T1 is the temperature of the first reservoir, and this is log natural of V2 upon V1, which is equal to log natural of V2 minus log natural of V1. Okay. Then we go to step 2. Step 2 is adiabatic. Adiabatic expansion. Adiabatic expansion of the gas from this set of variables to this set of variables. Okay. All the variables are changing. P2 to P3, V2 to V3, and T1 to T2. Okay. And in this adiabatic expansion of the gas from this to this, we have already obtained an equation like this. W23 is equal to nR T1 minus T2 divided by gamma minus 1. Okay. So T1 is greater than T2, gamma is greater than 1, so it's all positive, and gamma, I give you a reminder that this is the ratio of the molar specific heat as constant pressure and constant volume, which has got to be equal to greater than 1, because in CP there has to be some work done in expansion, the volume changes. Okay, and in CV there is no change in the volume, and therefore the work done is equal to 0, and therefore the gamma is equal to CP minus CV is greater than 1. So we obtain this set of equations for the expansion part from 1 to 2 and 2 to 3, and I just named them equations A and B. Now the third part from 3 to 4, which is an isothermal compression. Okay, from this set of variables to this set of variables, and like we obtained 1 to 2, similarly in 3 to 4 we write the equation as nRT2 log natural of V3 divided by V4. Okay, which is log natural of V3 minus log natural of V4. Okay, so we obtain equation C. for the work done from point 3 to 4. Next step is an adiabatic compression, and this adiabatic compression we move from this set to this set of values. Okay, so writing on the same lines like this, we obtain it as the work done 4 to 1 as nRT1 minus T2 gamma minus 1 divided by gamma minus 1, and the total work done W is equal to this plus this plus this plus this. Okay, now you find that 2 to 3 nRT1 minus T2 gamma minus 1. Of course, this is minus and this is minus because it is the work done otherwise. Okay, so this 2 to 3 and 4 to 1, they cancel out, and what is left with us is nRT1 log natural of V2 upon V1 minus nRT2 log natural of V3 over V4. So now we define the efficiency. Like before, the efficiency heat of the engine was defined with the work done divided by the heat that is reservoir 1, and that becomes equal to 1 minus Q2 upon Q1, which we have done already. So using that, I can write this equation finally as like this: 1 minus T2 over T1 log natural of V3 upon V4 divided by log natural of V2 upon V1. And now let us see and simplify it to a simpler result. Now from 2 to 3 or 4 to 1, we have adiabatic processes, and for the adiabatic process we have this equation: T1 V2 gamma minus 1 is equal to T2 V3 gamma minus 1. From this equation I can write V2 upon V3 gamma minus 1 is equal to T2 upon T1, or V2 upon V3 I can write as T2 upon T1 raised to the power of 1 divided by gamma minus 1. So this I get as an equation which I call equation E. And similarly, for the second process, adiabatic process where there is compression, I can write a similar equation over here, and from this equation V1 upon V4 is equal to same T2 upon T1 raised to the power of gamma minus 1, which shows F, equation F. So from these two equations we find that V2 upon V3 is equal to V1 upon V4, or we can write I bring V3 here, V1 here, and V3 upon V4 is equal to V2 upon V1, which I substitute in this equation which we have derived before, and we find that this term and this term both are the same terms, and so therefore they cancel out each other, and what I am left with, the efficiency is equal to 1 minus T2 upon T1. Okay, so this is the final result that we obtain in the case of the ideal Carnot engine using an ideal gas which is rarefied. That means its density is small, the temperature is high, and the pressure is low. It's the ideal gas situation in which the best fuel, and where we have got the best results for the Carnot engine or the Carnot cycle, where we come back to point 1 through the adiabatic expansion, isothermal expansion, adiabatic expansion, isothermal compression and adiabatic compression, and we find that eta is equal to 1 minus T2 upon T1. So to substantiate that about the Carnot engine, where the efficiency was given as was found to be 1 minus T2 upon T1, we talk about a Carnot theorem. The Carnot theorem has a couple of statements. One of the statements is redundant, the B part, that the efficiency of the Carnot engine is not a function of the working substance, which is vivid from this relation itself, because it depends upon the source and the, sink and the source temperatures, okay, and nothing else. So naturally, this is that used to be one of the relevant things at the time of Carnot, but it is not relevant if you give logic, use logic, and use this relation, eta is equal to 1 minus T2 over T1. But the first part, what he said and what he claimed and what he challenged, that if there are two reservoirs T1 and T2 working as a source and sink respectively, so between these two temperatures, no engine, no possibility of an engine of having an efficiency more than the efficiency of the Carnot engine. Okay, so to do so, we just take a situation where we have a source and sink working at different temperatures. T1 is the temperature of the source, and we don't care about this one, and we have two engines, I and R. I is an irreversible engine and R is a reversible Carnot engine, and we consider that I acts as a heat engine and R acts as a refrigerator. Okay, so what happens? I here absorbs Q1, delivers W dash as work done, and releases Q1 minus W dash to the sink. On the contrary, the reversible Carnot engine R returns same Q1 to the source, taking Q2 from here, from the sink, and requiring a work W is equal to Q1 minus Q2 to be done on it. Okay, so Q1 minus Q2 is the work which is to be done on it. Now suppose that the efficiency of the reversible Carnot engine is less than that of the irreversible engine. Let's take this thing. Just imagine. So, if R were to act as an engine rather than a refrigerator, it will give less output than that of I. That is, W is less than W dash for a given Q1. We discuss more. With R, the reversible Carnot engine acting like a refrigerator, Q2, which is equal to Q1 minus W, is greater Q1 minus W dash. Okay. So, on the whole, the irreversible reversible system that we discussed extracts heat which is equal to Q1 minus W minus Q1 minus W dash, which becomes W dash minus W from the cold reservoir. The heat is extracted from the cold reservoir and it delivers the same amount of work in one cycle without any change in source or anywhere else. Okay. Now, if you look at this statement, which we have this argument, then this argument becomes a clear violation of Kelvin-Planck statement of the second law, and therefore it's not possible for any engine, for that matter, using any substance, to have an efficiency more than the efficiency of a Carnot engine. Okay, so this was part 1 of the Carnot theorem. And then we see that in a Carnot cycle, Q1 upon Q2 is equal to T1 upon T2. Okay, where there is no mention of any working substance at all. Heat, temperature, plus. Okay, so we find that eta is not a function of the nature of the system, the substance that we use there. So that way, in this long journey of series of lectures on thermodynamics, we have come to an end. We have learnt the zeroth law, which is the manifest of and clear definition for the first time. The temperature has been defined, although I will define the temperature in terms of the kinetic theory of gases again, which I am going to take up next. Then the laws that evolved before the zeroth law of thermodynamics came were the first law, which was the law of conservation of energy, and the second law, which shows that there are certain conditions which are not possible, and there are two statements. One was the statement given by Kelvin and Planck, and the other statement given by Clausius. Carnot, who was a great engineer, he came out long before these laws were there and the foundations of thermodynamics were laid by scientists. As an engineer, he established that the maximum efficiency that we can have is that of the Carnot engine, where the substance which he used was the ideal gas, etc. So that way we have discussed the macroscopic theory, where we have macroscopic variables, where all variables are measurable: pressure, temperature, volume, mass, number of moles, are the constitution of the mixture that we deal in. So I have enjoyed, because I have taught this subject of thermodynamics after very long time, and my notes were also devised, and I have now a better understanding of thermodynamics, although I don't know what is the correlate between the teaching of thermodynamics in physics and the teaching of thermodynamics in chemistry. So that is in the what we can say in that our big daughter chemistry, okay, for the thin parents physics, and they have developed their own notions, they have developed their own PV curves, the isotherms. We have a PV curve like this, they have a PV curve like this, simply that they have made use of what is called a graph paper, which is rather called single logarithm or double logarithm, whereas we deal in the linear graph paper. So thank you very much. Enjoyed. Hope you enjoy.